Section 14.6 is about something called directional derivatives and the gradient. So this is where the book is going to introduce the notation and the terminology for gradient that we've already talked about. Remember, if I have z is a function of x and y, the gradient of f is the vector whose component functions are the two partial derivatives of f. And of course, if I had w being a function of x, y, and z, its gradient would be the vector whose components were the three partial derivatives that we would get. Okay. And we've discussed the fact that if a function of two or three variables is differentiable, the derivative will be the gradient. We use the gradient to build our candidate for the local linear approximation. And of course, if that turns out to be a good linear approximation, then our function is differentiable and our gradient is the derivative. And the user-friendly quick criterion to check is if the partial derivatives are continuous, then your function is going to be differentiable. Okay, well, directional derivatives are going to be derivatives that are similar to these guys. It's going to turn out these are actually examples of directional derivatives. They're going to be derivatives of cross-sectional curves that we get to the graph of our surface. So let's just suppose I'm drawing the xy plane here. So this is just going to be the domain of my function, or the domain is some subset of it. If I have some point p naught with coordinates x naught, y naught that's in the domain. Okay. When I'm looking at the partials of f with respect to x and y, I'm essentially taking a look at these cross-sectional curves that I get. And we've been thinking about them so far as just intersecting the graph of this surface with a plane. So when I'm taking the partial derivative with respect to x, we would hold y constant. So we would look at the plane y equals y naught. We would simply slice our surface with that plane and then look at the cross-sectional curve. Another way I can think about that is right here, this horizontal line that I've drawn here in the xy plane as it's oriented here, that's the line y equals y naught. If I restrict the domain of my function to just be points on that line, then what that function is going to do is that's going to attach a height to points that are on that line. That's going to give me some sort of a curve. I don't know how well this is going to show up, but basically if we think of the z values as coming out towards us, that's going to lift points that are on that curve, on that line rather, to create a curve in 3 space. That's another way of thinking about that. So I can think of either slicing the surface with a plane, or I can think of restricting the domain of my function to being points that are on this line. And then once I get that curve that's in 3 space, I'm just going to rotate it so that you can see it here, then we would take the slope of the tangent line to that curve, and that's going to give us our partial derivative. Essentially what that's doing is that's calculating a directional derivative in the direction of increasing x. As I've drawn it here, that would be moving to the right. Of course, in 3 space, x increases as we move forward. Okay. Similarly, if I take the partial with respect to y, I'm holding x constant. I can think of that as taking the graph of the surface and just slicing it with a plane x equals x naught. I could also think of that as taking this line in the xy plane, whose equation would be x equals x naught, and simply restricting my domain to being that line to create a cross-sectional curve. And there, we're calculating the derivative as we move in the direction of increasing y. With this orientation, that looks like moving up. Of course, in 3 space, y increases as we move to the right. Okay. Now, if I think about it, there are lots more than just 2 lines that pass through this particular point. So I could have another line that passes through that point. Certainly, if I were to restrict my domain to be points on this line, I would get a curve in 3 space. It would be a cross-sectional curve. I could also think of that as intersecting the surface with a plane. If I just take the plane that's the extrusion of this line, the intersection of that plane with the surface would give me that same cross-sectional curve. Okay. And I could talk about, well, how are things changing in that direction? Now, why might this be useful? Well, let's think of a couple examples. Let's suppose that I've got temperature is a function of x and y, so that the output of my function isn't a spatial dimension, it's not a height, it's the temperature. We've got a heated floor, okay? And I'm standing here and my feet are cold. And so I want to say, okay, I'd like to move to a place where my feet will be warm. I suppose I could put socks and shoes on, but no, I'm just going to move to a place where the floor is warmer. So if I move in this direction, does the temperature increase or decrease? If I move in this direction, does the temperature increase or decrease? If I move in this direction, does the temperature increase or decrease? And of course, I've got the opposite direction as well, okay, for all of those. Okay. So I'm sort of looking at, as I change my position on the floor, how does the temperature change? Now I can think of directional derivatives even if the third dimension is a spatial dimension, even if I do have z being a height function. So if I'm standing on a mountain, okay, and I'm sort of like, okay, I need to be walking, okay. Well, if I go this way, now I'm not assuming that the ground I'm standing on is flat. If I come forward, is my elevation going to increase or decrease? If I move to my left, it looks like your right, is the elevation increasing or decreasing? And I might be concerned with, how do I need to position myself? Let's say I want to get to the top of the mountain. How do I need to position myself so that I'm moving up, but I'm moving up at a steepness that I can handle? If I have a sheer cliff, unless I have my rock climbing gear with me and a partner for safety, and it's not too hard of a climb, I might want to look for a different path. So it would be measuring the steepness as I face different directions and think about moving along that mountain. Okay. So that's essentially what we're trying to calculate, and here's how we'll go about doing it. What I'm going to do, since we're creating this curve by just restricting the domain to be points on the line, is I'm going to parameterize my line. Okay. So I'm going to let u be a unit vector. I'm going to make sure that I parameterize my line using an arc length parameterization, because I don't want the speed with which I parameterize the line to screw up my results. Okay, so I'm going to let u be a unit vector, and I'm going to place it with its tail at point P naught, so that I'm going to parameterize my line as starting at P naught. P naught will be my starting point. U will be my direction vector. So I can say R of S would be X naught, Y naught. That's my starting point written as a vector, plus S copies of U1, U2. So the components of U will let me very creatively U1 and U2. So that's an arc length parameterization of this line where I'm using this unit vector as my direction vector. Okay, excellent. Then the curve that I get is f of R of S. That's going to be the curve I get by applying this function to points that are on this line. Okay. And if I take the derivative with respect to S of f of R of S, that's going to be giving me the slope of the line that's tangent to that curve. Now, if I'm concerned with what's happening at this point, I would evaluate that when S is equal to 0. That's because if S is 0, we're at our starting point. Okay. Notice that's calculating the direction as we go, how the z values would change as I moved in this direction. If I wanted to calculate things in the other direction, I would use negative u as my direction vector. Okay. So I'm saying as I go in this direction, how does my z value change? And that is different from going in this direction. So it's not just the line, it's the oriented line that we are plugging into our function before we calculate the derivative. So this would be the directional derivative of f in the direction of u at point p naught. That was a mouthful. You'd think there would be some notation for that, and there is. It's the directional derivative in the direction of u of f at the point p naught. We write a capital D, subscript the vector u, and this must be a unit vector. We use a unit vector to specify the direction so that the length of the vector doesn't mess up our calculations. Directional derivative in the direction of u of f at p naught. We often read that as duff because it looks like duff. Okay, excellent. So that's what we are going to be calculating. So let's try a specific example. And you can see why this section is coming right after we learned the chain rule, because that's exactly what we're doing. We're taking the derivative of a function composition. Okay, so we've actually been going for a little while in this video. I think I'm going to end this video here. Keep this formula up. I'll probably move it up to this section of the board. Next video, we'll start with a specific example.